Hi, my name is Shruti Narayanan, and today I'll be presenting the paper on the reliability of coverage-based fuzzer benchmarking published at ICSE 2022. So consider this situation. We run two fuzzers on the same exact software program for several hours, and at the end of the experiment, both report the same result. They both found zero bugs. So from a securities perspective, that may sound good, but from a benchmarking perspective, this can be a problem. Even a completely ineffective fuzzer could also find zero bugs. So bugs alone often don't tell us which fuzzer is better. This happens frequently in practice because real vulnerabilities are relatively rare. And because of this, fuzzing research typically compares fuzzers using code coverage, which measures how much of the program a fuzzer explores. So before we talk about the paper, let me quickly explain what fuzzing is. Fuzzing is an automated testing technique where we repeatedly run a program with many different inputs. A fuzzer generates or mutates inputs and feeds them into the software program. And if one of those inputs triggers a memory error, crash, or other unexpected behavior, it's found a bug. So these bugs are often detected using tools called sanitizers, such as Address Sanitizer, which automatically detects memory safety violations. Modern fuzzers are usually coverage guided, meaning they keep inputs that explore new parts of the program. So this helps the fuzzer gradually explore deeper parts of the code. So why do you think fuzzers generate thousands or millions of inputs instead of just a few carefully chosen ones? It's because bugs often appear only with very specific or unexpected inputs. So if fuzzers explore programs by executing code, how do we measure their effectiveness? The most common answer is code coverage, and the intuition for this is simple. You can't find a bug in code that you never execute. If one fuzzer explores more parts of a program than another, it could seem reasonable to assume that it has a better chance of finding bugs. Coverage also has practical advantages. It's easy to measure and it gives continuous feedback during fuzzing, and it works even when bugs are rare. So because of this, many fuzzing papers evaluate new fuzzers primarily using coverage. If a fuzzer explores twice as much code, do you think it will necessarily find twice as many bugs? And this is the type of question that this paper investigates. So coverage and bug discovery often show a strong correlation. So fuzzers that explore more code tend to find more bugs, but correlation alone is not enough for benchmarking, and what we care about really is ranking the fuzzers. And even with strong correlation overall, coverage and bug counts can still disagree about which fuzzer is best. So, for example, fuzzer A has high coverage but ranks below fuzzer B in the amount of the bugs found. So, now that we understand the motivation, let's see what this paper actually contributes. First, the authors introduce a different way of evaluating fuzzers. Instead of only measuring correlation between coverage and bugs, they measure agreement, which is whether coverage-based evaluation actually produces the same conclusions as bug-based evaluation. Second, they run a large-scale empirical study using many fuzzers, programs, and repeated experiments to measure how often these two evaluation methods agree or disagree. And third, based on their findings, they provide practical recommendations for how fuzzing experiments should be designed and evaluated. And finally, they make their experiments reproducible by releasing the infrastructure and data they used. So up to now, we've been talking about this idea that coverage is used as a proxy for bug finding. So the author's move is to say, don't just ask whether coverage and bugs are correlated, ask whether they produce the same conclusions about fuzzer performance. So they call that agreement, and they split agreement into two forms because people benchmark fuzzers in two different ways. The first is ranking agreement. This is when you take, say, 10 fuzzers and you order them from best to worst using coverage. Then you order them again using bugs found. So ranking agreement asks if these two orderings line up. So concretely, if coverage says A is number one, B is number 2, and C is number 3, does bug finding say the same thing? Or does bug finding flip the order? Like B is number 1 and A is number 2. Even these small flips matter because it changes who looks the best. And the second is superiority agreement, and this is the one that matches how research claims are usually written. So most papers aren't trying to rank every fuzzer every made, they're just trying to justify the claim that our new technique beats the baseline. So superiority agreement asks, if we compare two fuzzers, A versus B, does coverage say A beats B, and does bug finding also say A beats B? And importantly, only when the difference is large enough that it's statistically significant. That statistical significance part matters because fuzzing is noisy, and you can get random wins just from luck in one run. So the authors only count superiority when the evidence is strong enough. So in short, ranking tells you whether the overall leaderboard matches, and superiority agreement tells you whether my fuzzer beats the baseline, stays true when you switch from coverage to actual bugs. So the next question is, what did they measure and how did they run the experiments to test it? So this study is designed as a large-scale fuzzing experiment using the FuzzBench evaluation platform. So at a high level, they evaluate 10 different fuzzers across 24 real-world C programs. So these programs come from OSS Fuzz, which is Google's large-scale continuous fuzzing infrastructure for open source software. So the programs include widely used software libraries and tools that have already been used as benchmarks in fuzzing research. Now, fuzzing experiments are highly non-deterministic. Because fuzzers rely on random input generation and mutation, two runs of the same fuzzer on the same program can produce different results. A fuzzer could get lucky and discover a bug early in one run, but then miss it entirely in another run. So to account for this randomness, the authors repeat every experiment 20 times. So for each combination of a fuzzer and a program, they ran 20 independent fuzzing campaigns and later averaged the results across those runs. So each fuzzing campaign runs for 23 hours, which is a standard runtime used in fuzzing evaluations. So this gives the fuzzer enough time to explore deeper parts of the program instead of just the shallow code paths that are easy to reach. So if we multiply all of this out, which is 10 fuzzers, 24 programs, 20 trials each, and 23 hours per trial, the total compute time adds up to roughly 13 CPU years of fuzzing. So all of these experiments are executed using FuzzBench, which is an automated benchmarking framework specifically designed for evaluating fuzzers in a consistent and reproducible way. FuzzBench handles building the fuzzers, running the campaigns, measuring coverage and crashes, and storing the results. The experiments also use existing OSS fuzz harnesses and seed corpora, which helps reduce experimenter bias. In other words, the authors aren't handpicking inputs or modifying the setup to favor one fuzzer over another. Overall, this setup allows them to systematically compare coverage-based and bug-based benchmarking across many fuzzers, programs, and repeated trials. So before we look at the results, we need to be clear on what they measured because the whole paper is about comparing coverage-based evaluation to bug-based evaluation. So on the coverage side, the primary metric is branch coverage, which is basically saying how many control flow branches the fuzzer executes over time. Branch coverage is standard for coverage-guided gray box fuzzing, and it's usually considered a strong proxy because it captures control flow and not just which lines ran. They also include two supplementary coverage metrics, edges and paths, as reported by AFL-style fuzzers. AFL is American Fuzzy Loop, and it is one of the most influential gray box fuzzers, and lots of later fuzzers are AFL-based or AFL-inspired. Edges are often used as rough proxy for branch coverage and paths. The number of unique paths show up in a lot of fuzzing papers, even though it has known issues. Later in the paper, they actually use this to argue that path-based metrics should probably be abandoned because the agreement is especially weak there. On the bug finding side, their main metric is the number of unique bugs found, and this is where they do more work than a lot of fuzzing evaluations. A more naive approach would just count crashes, but crashes are messy and the same underlying bug can generate tons of crash reports. So they do aggressive reduplication. First, they automatically cluster crashes using a cluster fuzz-like approach based on crash type and the top stack frames, and then they manually clean up remaining duplicates. So in total, they go from hundreds of thousands of crashes reports down to few hundred clusters and then to a couple hundred truly unique bugs. Their second main bug metric is time to error, which is how long it takes for the fuzzer to find the first bug, because some papers care more about finding something fast than find a lot eventually. And as a supplementary metric, they also use unique crashes, which is common but less meaningful than unique bugs. So one subtle design choice is that they measure both coverage and bugs on the same buggy program versions. So they avoid the clean program assumption where coverage is measured on a patched version that doesn't match the buggy one. So RQ1 is coverage associated with bug finding at all. Because if coverage wasn't even correlated with bugs, the whole proxy idea would collapse immediately. The authors confirm what most people in fuzzing already assume. Coverage and bug discovery are strongly linked. On the left, this is figure 6 from the paper. So each little plot is one benchmark program. As an average number of covered branches increases during a campaign, the average number of bugs discovered also increases. And notice the y-axis is on a log scale, which already hints the relationship isn't perfectly linear. So the main point is across most programs, the dots form a very clear upward trend, meaning the more code you cover, the more bugs you tend to find. So on the right, figure 7 summarizes this using Spearman's row, which is a rank-based correlation measure, and they use Spearman because the relationship looks monotonic, but is not strictly linear. The headline result is that the average correlation between branch coverage and number of unique bugs is about 0.915, which they categorize as very strong. They also show similar values if you use edges or AFL style paths as the coverage metric. So at this point, if you only cared about correlation, you would conclude that, great, coverage works as a proxy. But the paper's whole argument is that this still doesn't tell you whether coverage is reliable for deciding which fuzzer is actually better. And that's where agreement comes in next. So now the question becomes, if correlation is extremely strong, why do coverage-based benchmarks still disagree with bug-based benchmarks when ranking fuzzers? So this is why strong correlation can still misrank. And so I'm going to make this logic as explicitly as I can. If correlation is above 0.9, your instinct is coverage must be a reliable proxy, so what's the issue? But the issue is that correlation is a global relationship, but benchmarking is a comparative judgment. So here are 3 ways you can get strong correlation and still pick the wrong winner. So scenario 1 is if there's similar coverage but different bug exposure. So 2 fuzzers might reach roughly the same amount of code, but one produces inputs that more often satisfy the exact conditions needed to trigger faults. So bug count differs even if coverage doesn't. Scenario 2 is there small coverage differences that don't map to bug differences. Correlation doesn't say that a small coverage advantage guarantees a bug advantage. In fact, if differences are small and noisy, coverage can flip who looks better even if bug outcomes consistently favor the other fuzzer. And scenario 3 is where coverage happens matter. So coverage is not uniform, and one fuzzer might cover more total code, but spend that coverage on areas with fewer or harder to trigger bugs. Another could cover slightly less code, but spend it in riskier or more bug-dense code and produce more unique bugs. So the right question isn't, is coverage correlated? It's, does coverage lead to the same conclusions we could get if we evaluated fuzzers by actual bugs? So that's exactly what they test next with agreement metrics. Agreement is only moderate. So RQ2 is the core result. How much do coverage and bugs agree on conclusions? So they report agreement in Figure 8A, and there are two headline messages. And first is that ranking agreement is only moderate. So for branch coverage versus unique bugs, the ranking agreement is around 0.498. So that means the leaderboard you get from coverage is only moderately aligned with the leaderboard you get from bugs. So this means that coverage is not consistently producing the same ordering of fuzzers as bug discovery does. Second, superiority agreement shows meaningful disagreement when they compare two fuzzers A versus B and only count cases where the difference is statistically significant. Coverage and bugs can still disagree on who wins. For branches versus bugs at p less than or equal to 0.05, the disagreement proportion is about d approximately equal to 0.113, meaning in about 11% of programs, you could get a different winner depending on whether you judge by coverage or by bugs. Across other metrics and thresholds, they show disagreement often lands in the 10 to 20% range, depending on the setup. And they also highlight one special case. When you require very strict significance for both metrics, like p is less than or equal to 0.0001, then superiority agreement becomes strong, like 0.875 in that strict setting. But notice the implication. You get very strong agreement only when you're looking at the subset of comparisons where the evidence is overwhelmingly strong on both sides. So the takeaway is not that coverage is useless, but that coverage only benchmark is not reliably equivalent to bug-based benchmarking, and it can flip winners often enough to matter. So this is why AFL number of paths are especially bad. A lot of fuzzing papers still report AFL's number of paths, basically the count of unique execution paths AFL believes it has discovered, and people sometimes treat it like progress, but the authors argue that this is especially unreliable. When they compute agreement, number of paths consistently has the weakest agreement compared to branches and edges. In some settings, the agreement is minimal, meaning the conclusions you draw from paths don't reliably match bug-based conclusions. And this matters because it's extremely tempting to write that our technique increases number of paths, therefore it's better. But this paper is basically saying that inference is especially risky. So their recommendation is don't use AFL number of paths as a benchmark metric for performance claims. If you want a coverage metric, use something more standardized and meaningful like branch coverage, and ideally report bug outcomes too. So agreement does not increase over time. RQ3 asks, does agreement improve over time? And in other words, maybe coverage-based rankings are unstable early on, but if you fuzz long enough, coverage rankings will converge to bug rankings. So they measure agreement throughout the campaign and not just at the end. So the answer is basically no. Longer fuzzing does not fix the problem. Ranking agreement doesn't steadily climb toward almost perfect, it stays moderate. It might move a bit, but it does not converge in the way you'd hope if time were the missing agreement. And superiority, again, the my fuzzer beats baseline style claim does not show the kind of improvement over time that would make coverage only benchmarking trustworthy. So you can't just respond to this paper by saying we ran it longer, so coverage is fine. Longer runs give more data, but they don't guarantee that coverage-based conclusions will match bug-based conclusions. So can we trust 1-hour benchmarks? RQ5 asks, how stable are rankings as you increase runtime? They compare rankings at earlier times to the ranking at 23 hours. And the result is that short runs can absolutely mislead you. So around 1 hour, the agreement with the 23-hour ranking is only moderate. So that means a fuzzer that looks top tier can drop later, and a fuzzer that looks mediocre early can climb later. And this is not only a coverage issue. They show instability even when ranking by bugs, because bug discovery can be bursty. One lucky early hit can distort the ranking, and some fuzzers only pay off after they've explored enough internal program state. But as the runtime increases, agreement improves. By around 12 hours, the rankings strongly agree with the 23-hour rankings. So their recommendation, based on this evidence, is that extremely short benchmarks like 1 hour are risky for strong claims, but something closer to half-day campaigns is much more trustworthy, at least in their setup. Before RQ6, I want to translate the statistics into easier to understand language because the paper uses several measures. So Spearman's row is a rank correlation and is asking if one metric says fuzzer A is higher than fuzzer B, does the other metrics tend to stay the same? So row is used for ranking agreement. Kappa is used for a superiority agreement. So it measures how often two decision systems agree beyond what you'd expect by chance. So here it's used for whether A beats B matches between coverage and bugs. A p-value threshold is how strict you are about only counting a win when the evidence is strong. Smaller p means stricter, p is less than or equal to 0.001. 0001 is extremely strict. The disagreement proportion D is the most interpretable, and it's literally what fraction of benchmark programs flip the winner depending on whether you use coverage or bugs. So when you hear D is 0.113, that's about 11% of programs disagree on the winner, and that's why the paper treats this as a practical reliability problem. So at this point, someone could say that fuzzing is noisy and maybe this disagreement is just randomness and maybe the measurement pipeline is unstable. So RQ6 is the authors doing sanity checks to show that the mismatch is real. So the first sanity check is coverage stable versus itself? They take their larger data set, split trials into two independent groups, and compare coverage rankings from one group to coverage rankings from the other. So the agreement is very strong, and that means coverage isn't randomly reshuffling the leaderboard every time, and coverage evaluation is internally consistent, and that is shown in the figure on the left. Sanity check 2 is, do bug metrics agree with other bug metrics? So they compare bug-based metrics like unique bugs, time to error, and unique crashes. So the agreement is strong, and this means that the bug metrics mostly tell a consistent story with each other. So that is in the figure in the middle. And then sanity check 3 is, do coverage metrics agree with other coverage metrics? They compare branch coverage with edges and paths. So within the coverage family, an agreement is generally high again. And so if coverage agrees with coverage and bugs agree with bugs and coverage metrics agree with each other, then the mismatch is not the evaluation pipeline being broken, and it's a mismatch between what coverage measures and what bug discovery measures. So they also test a practical experimental design threat, the number of benchmark programs. With very few programs, agreement varies wildly from negligible to very strong, meaning you can get almost any conclusion depending on which small set you happen to pick. But once you get around 10 plus programs, the variance tightens and they recommend not benchmarking with fewer than about 10 programs. So RQ6 is basically the author saying that this disagreement is not a fluke and it persists under stability checks and it has clear experimental design implications. So why can coverage correlate strongly with bugs overall, but still fail to pick the right winner often enough to matter? So the paper's explanation is basically coverage measures reach, but bug discovery requires exposure. Reaching a code location is not the same as triggering the fault condition. So think of fuzzing as a pipeline with three gates. Gate 1 is reach the location. This is what coverage tracks. You executed the branch, you hit the line, you traverse the control flow edge. Coverage says you made it here. So gate 2 is satisfy the trigger condition. Coverage does not measure this, so many bugs only happen when the program is in a very specific state, and that state could depend on deep structural properties of the input, like lengths matching internal allocations in a particular way, or sequences of operations that set up a dangerous condition. So for example, a parser might be executed every time, so it's covered, yet the bug only triggers when the specific optional field is present and a length variable causes a boundary condition. And gate 3 is the sanitizer or crash oracle fires. So in this paper, sanitizers like address sanitizer are the oracles. So to count a bug, you need an input that not only reaches the code, but reaches it in a way that violates memory safety or triggers a detectable failure. So two fuzzers can look similar in gate 1, similar coverage, but different differ massively on gate 2 and gate 3. So one fuzzer might be great at getting new branches by producing weird inputs that pass shallow checks, but it might be poor at producing valid enough structured inputs that trigger deep logic. Another fuzzer might cover slightly less code overall, but is much better at generating structured inputs that satisfy constraints and therefore expose faults. So that is how coverage can correlate overall, but still fail as a reliable scoreboard for winner decisions. So here's what the paper argues you should actually do differently after reading. The authors basically say stop treating coverage as a standalone scoreboard. Coverage can still be useful, but if your goal is to claim that your fuzzer is better, you need a evaluation design that doesn't accidentally state the wrong winner. So their recommendations are these few practical rules. First is to scale your benchmark enough to be meaningful. They recommend at least around 10 programs, and with too few programs, conclusions are unstable and highly sensitive to the specific targets chosen. More programs reduce the risk of winning. Second is to run enough trials, and they recommend around 20 trials per fuzzer program pair. And fuzzing is because fuzzing results are noisy and single runs are not evident. So repetition is how you distinguish real differences from randomness. Third is don't run toy length campaigns and pretend they represent ground truth. Based on their RQ5 results, 1 hour rankings can differ substantially from 23-hour rankings. So fourth is to report both coverage and bug outcomes. So this is the paper's thesis pretty much. If coverage and bugs can disagree on winners, then reporting only coverage is risky. Fifth is to avoid fuzzer-specific junk metrics like headline results. So they specifically call out the AFL number of paths. If the metric has especially weak agreement with bug outcomes, it shouldn't be used as primary evidence that one fuzzer is better. And six is to be statistically honest and reproducible. So they recommend non-parametric statistical methods and reporting effect sizes because fuzzing result distributions are often non-normal and heavy-tailed, and they emphasize releasing artifacts, configs, data, and tooling so results can be validated and reproduced. So the three takeaways is first, coverage and bugs are strongly related. In their data, fuzzers that cover more code tend to find more bugs. That validates why coverage has become a common proxy in the first place. Second, and this is the contribution, benchmarking is a decision problem, not a trendline problem. When you ask which fuzzer is better, coverage-only benchmarking only moderately agrees with bug-based benchmarking, and in a non-trivial fraction of cases, often around 10 to 20%, depending on thresholds. You could crown a different winner depending on which metric you used. And third, they turn this into a practical evaluation checklist. So use enough programs, enough trials, long enough campaigns, report bug outcomes alongside coverage, avoid unreliable metrics like number of paths, and publish artifacts for reproducibility. The takeaway is don't treat coverage as a sufficient evidence that your fuzzer truly finds more real bugs. Coverage is useful, but not always reliable as a scoreboard that decides who wins.